So as I was saying, this is what you get when you combine those two. So now for us to combine this in order to get the polynomial function, I'm going to be using the box method just because I find it a lot easier. So this is how you use the box method. I'm going to be placing all of my little terms right here, and this one's going to go on the side. 4. Now I draw a box. And draw boxes inside of it too. And we multiply them. We basically, like, you'll see what I mean. So x squared and x squared, you get x to the power of 4. And x squared and 4, you get 4 x squared. We're basically kind of combining them. So x squared, negative x and x squared will give you negative x cube, since you have a x plus another x cube. And negative x and 4 will give you negative 4x. Negative 6 and x squared will give you negative 6x squared. Negative 6 and 4 will give you negative 2. So you like add them. Okay, so we look at it, and as in this example, we can combine like terms. So we see that there's 2x squared, so we can combine negative 6x squared and 4x squared. If we combine them, that leaves us with negative x squared. And now we just write out our polynomial function from biggest degree to smallest degree as a normal polynomial would be written in, which that is x fourth minus x cube minus 10x squared minus 4x minus 2. This is our polynomial function that we get when we combined the zeros that we were given. This is what we get. This is what we get. And this is a polynomial function, and it's also written in standard form, but this is basically what we get. So to just go over it once again, we are given our zeros, we write them out just as given: x minus 2, x plus 3, x plus 2i, but the I always comes with its conjugated pair, so you write x minus 2i. When you set them equal to 0, you get x plus 2, you get x minus 3, you combine them, distribute the x's and combine them, combine like terms, you get your first function. Same as this, distribute them, combine them, and you get your second function. And then do the box method just to be safe. Combine anything that you can combine in there, and then you just write it down from greatest to least based on the power. And that is your polynomial function in standard form. Now, the next question, question 3, says, what are all asymptotes and removable discontinuities for the graph g of x, x cubed plus x squared all over x cubed minus 4x squared plus 4x? We have to sketch it, and can a horizontal asymptote be crossed? Well, we're about to find out. So let's first start off by writing down our function. So our given function g of x is x cubed plus x squared all over x cubed minus 4x squared plus 4x. So we are first going to graph this function to make it a lot easier. So let's graph it. So I'm just going to be graphing it here. Going to be placing the numbers based on the calculator graph so that we can get the points that we really need. So now that we have that, we have to see all of its asymptotes and if there are any removable discontinuities. So let's first start off by our horizontal asymptote, which we're going to represent with an H, horizontal asymptote. So not just graphically, but mathematically, you can find the horizontal asymptote by simply taking the largest power from the top, which would be x cubed, and the largest power from the bottom, which would be x cubed as well. And you take that x cubed and you divide that. So you divide the biggest one on the top by the biggest one on the bottom. When you divide that, that's simply going to be 1 over 1, because when you divide the exponents, subtract, and 3 minus 3 is 0, so you're left with 1, 1. And when you divide that, you get 1. So the horizontal asymptote is at y equals 1. So here it is. Your little imaginary line, your horizontal asymptote when it equals 1. And for vertical asymptote, we're going to represent with a V. Vertical asymptote. It's kind of the same similar way, but instead, it's looking at the X. So it's like a little line where they cross. The asymptotes cross. This is where they cross. But the graph itself never touches that point. It never touches to it. It gets really close to it, but it never really quite touches that point. So we can kind of see that it's at x equals to 2. So that's our vertical asymptote. And we get that by 2x minus 2 plus 1 x minus 2 equals 0. So we add a 2 to cancel that to equal to 0, and that's how you get 2. So you get 2. And there are actually no removable discontinuities. There's no removable discontinuity. because they all just keep on going up and they keep on going to the side. So once again, this is how you find the asymptotes in the removable discontinuity. And remember, the horizontal and vertical asymptote, they always get close to them, but they never actually touch them. They never do. So now let's look at question number 4. It says, which describes the end behavior of the graph f of x equals negative 4x cubed minus 5x plus 1. And I'm going to be showing you 4 more scenarios of how end behavior works. So let's first start off with this one. So let's write down what we're talking about here. We're talking about end behavior with the equation negative 4x cubed minus 5x plus 1. So to find the end behavior, we have to graph this, which is going to be the best way for us to actually see the behavior and how it ends, how the equation acts on both sides of the graphs.